Hey everyone, and welcome. Today, we're diving into a really big shift in science education. It's a whole new blueprint designed to move students from just, memorizing facts to actually doing science. All right, let's get into it.
So, just for a second, I want you to think back to your own science classes. What do you remember? Was it a ton of reading from a textbook, memorizing the periodic table, or learning all the parts of a cell? Yeah, for a lot of us, that's what it was. But what if that whole approach kind of misses the entire point of what science is all about? This quote from the National Research Council really hits the nail on the head. It's basically saying that if we only teach the what, the facts, but we totally ignore the how we discovered those facts, then we're not just giving an incomplete picture. We're actually misrepresenting what science even is. So the big question is, how do we fix that? Well, the answer comes in this new framework called the Next Generation Science Standards, or NGSS for short. The best way to think about it is like a brand new blueprint for how we build a science education from the ground up. And this blueprint is built on three big dimensions that all get woven together. You've got your disciplinary core ideas, that's the key stuff you need to know. Then there are the cross-cutting concepts. These are the big themes that connect all the different fields of science. And then you have the science and engineering practices. Now, all three are super important, but we're going to focus on the practices today because they are the real game changer here.
Yep, we're diving deep into these science and engineering practices. You can think of them as the active ingredient in this new recipe for science class. This is the part that gets students to stop just sitting there and start actually doing things. It's not about what scientists know, it's about what scientists do.
So what's in this new toolkit? What does it actually mean to do science? Well, the framework boils it down to 8 essential practices. That's right, just 8. And here's the really cool part. These aren't just for, advanced high school students. They're designed to be learned and built upon every single year, starting in kindergarten all the way through graduation. The whole idea is to empower all students to think and act like real scientists and engineers. We can kind of group these 8 practices into 3 main buckets. The first one is all about investigating. This is where everything starts, right? It's about curiosity, it's about learning to ask good questions, define problems that need a solution, and then actually planning and carrying out a way to find some answers. Okay, so once you've done your investigation and you've got all this stuff, this data, what do you do with it? Well, that brings us to the second bucket, making sense. This is where you build models to figure out what's going on, you dig into the data to find patterns, and you use the powerful tools of math to really understand the relationships you're seeing. And finally, science isn't something you do alone in a basement. The third bucket is all about communicating. You have to build explanations for what you found. You have to be ready to argue for your conclusions, using your evidence. And you have to be able to find, judge, and share information clearly. That's how science moves forward.
And what's really cool is that these practices also shine a light on a key difference between science and engineering. It really just comes down to your goal. If you're trying to answer a question about how the world works, you're doing science. But if you're trying to design a solution to a specific problem, well, you're doing engineering. Same toolkit, just a different mission.
So the really crucial part is understanding how these practices actually work in a classroom. They're not just a list of things to memorize. They are real abilities that need to grow and get more and more sophisticated over a student's career. Let's just take one practice as an example, okay? Developing and using models. So, in kindergarten, a student might build a really simple model, like using a toy car and a ramp to understand how things move. But by the time that same student is in high school, they're using that same core practice to build abstract computer simulations to model really complex systems and predict what's going to happen. It's the same idea, just way more advanced. And the framework is super intentional about calling these practices instead of skills. And there's a reason for that. A skill can be something you just do by memory, on autopilot. But a practice means you have to apply specific knowledge. You can't just analyze data. You have to know what data matters and why it supports your idea. It's knowledge in action. It's also so important to get this. These 8 things are not a neat step-by-step checklist. Real-world science isn't like that. These practices overlap and loop back on each other all the time. You ask a question, which makes you build a model, which leads you to analyze some data, which makes you ask a whole new, better question. It's a fluid, interconnected dance. Okay, so let's zoom out. Why is this shift so critical? Why are we moving away from the old textbook and memorize model that's been around for, well, forever?
Well, the impact is just massive. When students actually get to do science, it lights a fire.
It sparks their curiosity in a way that just reading about a topic never could. It shows them that science is this deeply creative and exciting process. And maybe most importantly, it gives them the thinking tools they're going to need to tackle the world's biggest challenges.
And let's be honest, those challenges are enormous. We're talking about huge things, like figuring out how to generate clean energy, how to treat and prevent diseases, how to deal with climate change. These aren't problems you can solve by just remembering facts from a book. They require a generation of innovators and critical thinkers.
So, I'll just leave you with this question to think about. What does our future look like when an entire generation comes out of school having spent years not just learning about science, but actively practicing it every day? What happens when they are fluent in doing science? The potential is just absolutely transformative.